The sun is to the right of the slit.
Too far. Move back. Just a little bit. Hold it. That's it.
Perfect, George. We've been adjusting a heliostat in order to bring sunlight in here in a steady beam. The lens produces a fixed image of the sun at the point where I'm placing this screen. The mirror on the heliostat is driven by a clock. It rotates about this axis, which we have carefully set parallel to the polar axis of the Earth. The mirror follows the sun. It is set to account for today's elevation of the sun above the horizon in such a way that it reflects rays from the sun parallel to the polar axis of the Earth, regardless of the time of day. Some of the reflected sunlight is intercepted by a fixed mirror behind the window in the periscope tube and is sent down toward another reflection at its lower end, which brings the sunlight into the lab. I had a slit here before. Let me put it back. What we have here now is a prism spectroscope. The continuum is interrupted by many dark lines of varying thickness and intensity. They are all parallel to the slit and signify the absence of slit images over various narrow wavelength bands. This exposure was made on one of the common color films. The eye can see the range indicated. Commercial color films are insensitive to the red above 6,800 angstrom units, but the eye responds to intense light up to 7,600 angstroms. Sunlight, of course, is quite intense. With infrared sensitive color film, the missing visible red portion, and even some of the invisible infrared light, exposes as red. We are not showing you the remainder of the spectrum below 6,800 angstroms, as exposed on this emulsion, because it misrepresents the colors in that range. This is a composite of the two exposures. The dark lines in the spectrum of the sun were first studied in detail by Joseph Fraunhofer and are named for him. By his own count, he saw 574 lines between here and here. Our knowledge of this spectrum has been greatly extended since Fraunhofer. Tens of thousands of Fraunhofer lines have been recorded. The most prominent dark lines have been assigned letter names. The study of this spectrum by Fraunhofer was by no means his only scientific work, but it is interesting to note that the more prominent of these lines played a major role in all his other work as reference marks. This outstanding experimental scientist produced the finest quality optical glass the world had seen up to his time. His lenses approached perfection. He put the optical industry on a scientific basis. And, what's more, he constructed the first high-quality diffraction gratings. Fraunhofer's life was spent in or near the city of Munich, in Bavaria. We took a trip there because a number of his original instruments and samples are preserved there, most of them in a large museum of science and technology, the German Museum. This is a sample of glass which Fraunhofer cut from some of his experimental melts. It is actually two samples from two different melts, polished to form a dual prism of common angle. He used it to compare the refractive and dispersive powers of two different glasses. The prism in the middle is made of crown glass. It's light green due to iron impurities, but quite uniform optically and free from internal strains. The two others are flint glass, reddish-brown because the red oxide of lead was a major ingredient for this type of optical glass. Flint glass has higher refractive and dispersive power than crown. Fraunhofer modified a surveyor's theodolite into the first precision spectrometer in the history of optics. He focused the telescope on a narrow vertical slit. The slit was very far away. Fraunhofer did not use collimating lenses. When its image was centered on the intersection of the crosshairs in the eyepiece, he read the telescope's angular position on a protractor, which was ruled on a silver circle. It has tarnished over the years. The vernier gave him a least count accuracy of 10 seconds of arc. Next, the prism was placed on the table in front of the telescope. Both the prism and the telescope were turned until one of the dark lines in the solar spectrum was both in minimum deviation and on the crosshairs of the eyepiece. Then the telescope's new angular position could be read on the vernier protractor. From the angle of minimum deviation delta for, say, Fraunhofer line F, he could calculate the index of refraction, N sub F, which his prism has for this radiation, but only if he also knew the value of alpha, the apex angle of his prism. He found this value too by using his telescope in theodolite to the same accuracy with which he knew delta sub F. Next, he measured delta for a number of different Fraunhofer lines using the same prism. Then he went on to do this for other prisms. He charted the refractive and dispersive powers of optical materials. Fraunhofer's personal notes are preserved in the library of the German Museum. On one of the pages, he tabulates refractive indices for a sample of flint, another of crown glass, and for water. Each column cites a value for a given monochromatic light, red at left to blue at right. 6 of the digits are significant figures. He published an important article on the solar spectrum, the dispersion of glass, and achromatic lenses. There is not enough time to describe all the experiments Fraunhofer discusses in his epoch-making paper. Let me just say that his precise values for the dispersion of flint and crown glass led him to design and then to produce achromatic lenses of the highest quality. He changed lens making into a science. He was a gifted draftsman and engraver. The plate from which this picture was struck was engraved by him. For his own use, he watercolored this print. This doublet lens has a diameter of 24 centimeters. That's 9.5 inches. One lens is flint and diverging. The second, crown and converging. Each of the 4 surfaces are ground to a different radius of curvature. The lens pair is set at a pre-calculated spacing. Not all lenses coming from Fraunhofer's workshop were large, nor did he confine himself to the production of lenses. He designed entire optical instruments. This is one of his achromatic microscopes. Such instruments were available for sale from the firm at which all his work was done and in which he became one of the partners. This is one of their theodolites. This pocket-sized nesting telescope for terrestrial use, for example, as an opera glass, was engraved by Fraunhofer and presented to a friend. During his brief lifetime, however, he reached his greatest fame for the astronomical telescopes he made. The tube is about 14 feet long. Everything in this telescope was designed by Fraunhofer, the lenses as well as the mount. The axle is set precisely parallel to the axis of the Earth. With this wheel and protractor, the optic axis of the telescope can be set to the elevation of a star above the horizon, and the elevation can be measured with precision. The polar axis is driven via gears by a self-regulating gravity clock. So, the telescope can follow a star. Once in the intersection of the crosshairs of the eyepiece, a star stayed there for hours. even at high magnification. The planet Neptune was discovered through this telescope. A telescope of similar dimensions was sent by Fraunhofer and his firm to Wilhelm Struve, a great astronomer who worked in Russia. Through Struve's work, it became the most famous telescope of the time. It is not known whether it still exists. Fraunhofer died in the year 1826, when he was 39 years old. At that time, he was designing even larger telescopes. In the year 1847, a large refracting telescope, built in Munich by Fraunhofer's successors in the same firm, was sent to Cambridge, Massachusetts, for use at Harvard College. It is still there today on its original granite base. It has the characteristic Fraunhofer mount, although the gravity clock has been replaced by an electric drive. It is over 20 feet long. It is occasionally used for astronomical observations even today. The telescope is so well balanced that it can easily be turned by hand. The aperture of the lens is 15 inches. Fraunhofer began by studying the dispersion of optical glass, which he had perfected himself. In the process, he discovered the dark lines in the spectrum of the sun. Soon, he was making the best optical lenses the world had ever seen. With this film, we honor the man who founded the scientific optical industry. The sun is to the right of the slit.
Too far. Move back. Just a little bit. Hold it. That's it.
Perfect, George. The Earth. The mirror follows the sun. It is said to account for today's elevation of the sun above the horizon in such a way that it reflects rays from the sun parallel to the polar axis of the Earth, regardless of the time of day. Some of the reflected sunlight is intercepted by a fixed mirror behind the window in the periscope tube and is sent down toward another reflection at its lower end, which brings the sunlight into the lab. We've been adjusting a heliostat in order to bring sunlight in here in a steady beam. The lens produces a fixed image of the sun at the point where I'm placing this screen. The mirror on the heliostat is driven by a clock. It rotates about this axis, which we have carefully set parallel to the polar axis of